Good afternoon, everybody. My name is Professor Seung-Bum Hong from KAIST Korea. I'd like to thank Session Chair and organizers to invite me through video conference. The title of my talk is Materials Imaging Initiative, Past, Present, and Future. The next slide shows a photo shoot of myself presenting the vision of M3I3, which I will present more detail in the following slide, which was included in KAIST Future Report 2031. So KAIST M3I3 Research Initiative is the Materials and Molecular Modeling, Imaging, Informatics, and Integration, and it has two big major components, including structured property library development at multiscale using machine learning and artificial intelligence with the help of imaging and visualization, and also the automatic synthesis of molecules and materials based on the recipe developed and 3D printing technology. In 2017, related to this vision, I set up my lab and I called it Materials Imaging and Integration Lab, and you will see the picture of my members in the slide. So as a promotion slide, we are hosting Asia Pacific PFM 2019 next year at Seoul National University with the help of local organizing committee, which includes Professor Taewon No, who gave a plenary talk in this conference, as well as Professor Cho Sung Hwang, Professor Chan Oh Yang, Professor Yoon Seok Kim, Professor Sang Mo Yang, and Professor Sang-an Lee. So a brief introduction of myself. I have a diverse background from industry, national lab, and academia. As I got my PhD from KAIST, I did my postdoc at EPFL, and I did a work at Samsung Electronics, spearheading the ferroelectric hard disk drive initiative, and then I moved to Argonne National Lab to do basic energy science, and then I returned to KAIST to teach graduate students. So let's start with the past of Materials Imaging Initiative. Hard disk drive is a prototypical information storage device which benefited a lot from materials imaging. In order to brief you with the basic principle of a hard disk drive, this is a schematic you can imagine inside your head. So you can simplify hard disk drive as two components, one being probe head and the other being medium, where those two components move in relation to each other to address the bits that are written in the media. So this is, in other words, mechanically addressable storage devices. In the history, hard disk drive was not the only one. As you can see, the turntable, which is now obsolete, but if you go to Barnes & Noble in the United States, people are now trying to buy this one again, where you have the polymer media and the musical information is encoded in the form of topographic variation. So the pickup, the magnetic pickup, is really a strain sensor like in atomic force microscopy. Now, Richard Feynman, who is a very famous physicist in the United States, already stated that there is plenty of room at the bottom, meaning nanotechnology or quantum technology will be the future buzzwords. And indeed, hard disk drive industry tried to accommodate that vision and made small hard disk drives as depicted in the slide. But as you know, the flash has beaten the competition. So now hard disk drives can be only found for archivized storage or cloud storage. At that time, people at IBM came up with a vision that AFM can be really transformed into a hard disk drive if we make the indentation very small at the atomic scale, and if we can make the slider at the scale of MEMS cantilever, and using the multi-probe scheme, they envision that they can have high data transfer rate. So this roadmap now, which is in history, shows how they developed the single AFM probe type of information storage device into multi-probe prototype and a real storage prototype where they could read and write an image file without a problem. Now people understood the challenge of this thermomechanical probe storage, which resembles the turntable because of the way they make indentation and how they read back by using mechanical deflection. They ultimately saw this would be an obsolete technology. So people began to think about alternative read-write mechanisms, and we were one of them in Samsung. And we were thinking, what about ferroelectric? Because if you look at the paper presented by Dylan Fung at Oregon National Lab, we were able to see the physical limit of ferroelectric storage if we can make up and down ferroelectric domain as 0 and 1. As you can see here, they were able to show that even 3-unit cell thick ferroelectric thin film can retain up and down polarization, and according to the Kittel's law, the domain width is proportional to the thickness, thereby showing us 10 terabit per square inch will be a reality if we're coming up with a matching system for this medium. So for those who are not familiar with ferroelectric materials, this is a one-slide introduction where perovskite structure is a prototypical structure for ferroelectrics, but it's not the only one. This is the easiest slide to show you how you can create a polarization up and down, left and right, and front and back by changing the position of the titanium that is rattling inside a oxygen octahedra. And ferroelectricity is coming from spontaneous polarization, which is being able to be switched by external field application. So you have hysteresis loop that you can see from the right side. And also, in addition to that, a bigger category is piezoelectricity. So piezoelectric coefficient will switch its sign upon change of polarization because polarization and D33 is linearly coupled. Now, in order to use these materials as media, we need a reading and writing mechanism. Writing mechanism is pretty simple because if you have 2 electrodes applying electric field, you'll be able to write in a local spot. But then the next question is, how do we read it? So if you use mechanical strain, as in the case of the IBM researchers, then the speed will be limited by the mechanical resonance, which is about megahertz range. So the idea Samsung came up when I was a leader was to use field effect transistor, which operates at gigahertz range. So the idea was to build source channel drain on top of a tip. So the key process idea presented by Professor Hong-Sik Park at Gyeongbuk National University was to reverse the sequence of making the channel on top of the tip by first forming the channel and then use part of the implantation mask to self-align the channel on top of the tip. So the processing results is history as well. As you can see, we were able to make a field effect transistor tip using MEMS process. So in this slide, you will see how we improve the spatial resolution of our field effect transistor probe by changing the geometry from very sharp tip to blunt tip, which is counterintuitive. And you will see that the electric field gradient will be sharper as you increase the dimension of your channel. So the result here shows that we were able to image the artificially written pattern like resistive probe as well as checkerboard pattern down to the spatial resolution of 25 nanometer, and this is at maximum 1 terabit per square inch. At that time was a minimum threshold to qualify as a future storage device. So you can see here the imaging process, the imaging development directly correlated with the information storage development. If you're not sure yet, I will show you how this can be transformed into some prototype of hard disk drive. We also did a lot of work on bit stability because people were worried, unlike in magnetics, the polarization formed by electric field may backswitch and you will have loss of memory. So we understood that charged dipole interaction is very important, and fully penetrated domains is the key to stabilizing the information you have written in your ferroelectric media. As you can see, with the help of Professor Yoon-Suk Kim at Sungkyunkwan University, we were able to patent this and also show that at 200 degrees Celsius, you can maintain the bits that you have written in the media. However, there was a problem with the wear and tear. As you can see, this was in contact. So the next big step was to see if we can do it in non-contact. As you can see from the tapping mode and non-contact mode AFM, you have a drastic improvement in reliability. So if you think about the hard disk drive, the biggest revolution was the ABS, which is the air bearing slides, which allows your slider to fly above your media at about 8 to 10 nanometer distance. And also another big hit was the invention of magnetoresistance, first being GMR and then being TMR, to increase the spatial resolution of the reader as well as its sensitivity. Now, as you can see from the ASTC technology roadmap, people in industry, in hard disk drive industry, sees heat-assisted magnetic recording being the next future technology, as well as heated dot magnetic recording, which is the combination of pattern media and hammer being the next big thing. And you can see the highest density foreseen by those technologies, 10 terabit per square inches. This is a schematic that shows how people have worked on perpendicular magnetic recording and then now changing to hammer, where they are adding laser in order to heat the media to soften the switching field and then write it easily and then put it at room temperature to increase the reliability. Now, ferroelectric hard disk drive, without the addition of those kind of laser, we envision could achieve those goals. As you can see, by changing the materials for the sliders from Altic, which is ceramic, to silicon, and changing the media from the composite layers of magnetic component to ferroelectric media. So we were able to combine the front-end processing from the silicon fab processing and the back-end processing of assembly of the components in the hard disk drive's assembly line. So you can see the prototype, and we show that at 7200 RPM, we were able to write a track of ferroelectric bits on ferroelectric media, which has the same size of 2.5 inches disk. And we were trying to understand how this was possible even in non-contact mode. So we mimicked that experiments using AFM and found that charge injection across the gap of the air could deposit enough charge to switch the bits in the ferroelectric media. So with that, we were able to file a patent, register it, but now Samsung has sold it to Seagate, so as you can see. So if you Google Seagate patent ferroelectric hard disk drive, our patents are now transferred to Seagate, as you can see from the first slide and the following slide in this presentation. So now I hope I convinced you that materials imaging visualization help design future information storage devices, so you can see the connection between imaging initiative and the applications. So let me start with the discussion of what visualization is. Now, in other words, it's observation, and it's the first step of science, like in the Renaissance science, as you can see. And it's ingredient of hypothesis. So scientific methods is really converging your hypothesis until you validate the hypothesis using experiments. And here experiments always includes measurement, and measurement includes observation. Now you will ask me, for example, then what do you observe? So here I would like to claim that we observed physical parameters as a function of space and time. So that could be field, and that could be order parameters. By observing those, what can we know? We can know the cause of a problem, for example. Why does fatigue occur in ferroelectric thin films, or degradation in resistive switching oxides? Why do we have dendritic growth of oxygen vacancies? Or why do we have dendritic growth of lithium in lithium-ion batteries? We can also know nucleation and growth of phases. By knowing that, we will be able to estimate the switching speed. We can also understand kinetics driven by thermodynamic forces, and then we can understand the efficiency of transduction, stability, and reliability. Okay, then how do we do that? So the key technique here is to design marker. So what kind of markers do we have? So in the next slide, I'm showing that we can use work function in the material as a marker to visualize dopant concentration. So one example is visualizing the resistive probe that we developed, which is field effect transistors, where you have NPN junction. And NPN obviously have different work functions. So work function can be a very nice marker, and you can see by visualizing the work function as a function of space, time, and also the processing parameters like annealing time, you will be able to understand the diffusion kinetics of the dopants inside your transistor. So then, what is an AFM? What is the contact mode atomic force microscopy that we use to visualize the topography, as well as, for example, the work function inside the transistor that I just described? So AFM, in a nutshell, is like a nanoscale finger where you use the repulsive force between the atom on top of your tip and the atom on the surface of your materials of interest, and get the feedback in terms of the deflection of your cantilever, and then use it as an error signal. So you can use constant deflection where you maintain the bending of your cantilever and move your actuator up and down, so the motion of your actuator replicates the topography, or you fix your actuator and measure the bending of your cantilever up and down, which we call constant height. So these are two very simple basic operational modes of AFM. So with that in mind, if you look at this schematic, you can split the vibrational signal in frequency domain to separate out the topography signal. So topography signal, if you think about it, the roughness as well as the scan rate, the maximum frequency component is about 2 to 3 kilohertz. And knowing that, you can put a low-pass filter at that region without perturbing anything there, and use constant deflection mode to maintain the same bending at that frequency, and then using constant height mode for agitation you induce by applying, for example, AC voltage, and create an artificial strain by piezoelectricity. Then you can look into polarization domains and topography at the same time, at the same spot. So knowing that basic principle, now we don't have to worry about topography and just focus onto this high frequency signal induced by AC voltage that we apply to the tip. So the simplest system here is up and down domains, like in the case for PZT that we use for electric hard disk drive. And if you apply AC voltage small enough not to perturb the state, then up and down motion of your media will be translated to vibration of your tip. So the sequence of your vibration will be parametrized by phase. So if it is 180 degrees phase shift, then it's up polarization. If it is 0 degrees phase shift, it is down polarization. And the amplitude of the vibration will represent the strength of your polarization according to the equation that relates the D coefficient, which is piezoelectric coefficient, with your polarization. So you can see with this in mind, you can pattern ferroelectric domains artificially by changing the amplitude and duration of the voltage. And like in the cartoon, you can create a nice donut-shaped amplitude image and 180 degrees phase reversal domain image in the face. So with this technique, you were able to apply it to the ferroelectric information devices, but also by using this technique, you can also measure and evaluate a newly synthesized ferroelectric organic crystals, which is now shown in this slide. So in collaboration with Professor Vinayak Dravid at Northwestern and Professor Fraser Stoddart at Northwestern as well, I was able to evaluate the flexible ferroelectric organic crystals using the technology or technique that I just introduced. But you can see this interesting story here. The paper that we worked on was accepted September 5th and published October 13th. And in between, there was a big event, as you can see in the next slide. October 5th, Serge J. Fraser Stoddart got his Nobel Prize in Chemistry, and they were giving the right to announce the news on Nature Communications, obviously because Nobel Prize news was a bigger one. So I was honored to be able to get this news out when I joined KAIST on the same date, January 12, 2017. And then later on this year, we had a workshop between KAIST and Northwestern, and 3 of us gathered together at KAIST and took a picture, as you can see in this slide. So research thrust is not only about scientific efforts, but also human network, also hanging around and brainstorming together. And that's a big fun part of the research, as I see. So now I told you we used piezo response as a marker to visualize the polarization, because polarization and piezoelectric coefficient is linearly coupled. We were thinking, can we use another marker to visualize polarization? For example, to enhance the speed of imaging. And obviously, if you look at this picture, it is not only polarization and piezoelectricity, but also screening charge that you can use as a marker. Now, the idea came up with Dr. Andreas Reloff, now who is a director at Los Alamos National Laboratory Center of Integrated Nanotechnology. And you see we were able to use AFM tip as a means to scrape the screening charge and collect the current to visualize the ferroelectric domain underneath. So here it looks like a conducting AFM, but we are not applying electric bias, so there is no driving force in terms of electric force, but you only push hard and scrape it. Now, if you push hard, you obviously have piezoelectric charge, but that charge is very minor if you compare it with the scrape charge. So in this slide, you will see the direct evidence that CGM creates more current than direct piezoelectric force microscopy. So the piezoelectric charge created by the force you apply through the tip will be a minor component in CGM. So if you look in the Nature Com paper published by a Spanish group, you will see the same materials were used, the periodically poled lithium niobate, and you will see very similar contrast. However, they were very careful to remove all the charge scraping component. So if you look into the Z-scale of their image, the current scale is femto-m, while our current image is in pico-m. So you can see there is 1,000 times difference, meaning in our image, the piezoelectric charge contribution is less than 0.1%. Another mechanism one can probably think of is when you have ideal surface without screening charge, you only have unscreened polarization in vacuum, for example, and your tip is the only source of giving the screening charge. In that case, it is not scraping. Now you are supplying the screening charge, and upon meeting the boundary, you will spit out the screening charge for one domain and accept the other screening charge. So you will have a switching event in space. So the current that you will see here is also very large, corresponding to 2pr displacement current. However, you are doing that in space. So we did that. We did this careful experiment in vacuum, and as you can see, you can have a very clear and repeatable current peaks at the domain boundary, which is also very large and is very reproducible, as you can see in the following slide. Now, but in ambient, it is not the case, as also evidenced by another group at University of Washington, Seattle, by my colleague Professor Jang-Yu Lee and his postdoc Isan. And you will see the contrast is slightly different than in the case of your displacement current. And we have put evidence of scraping in our supplementary information in PNAS as shown in this slide. So you can see on the left part of the slide, that PFM image is there, up and down domain. EFM amplitude and EFM phase shows very little contrast, meaning it is fully screened. And after we do the CGM on the right side, we collect a large current. And after we do that EFM, we see a very clear contrast, while we don't see much change in PFM, meaning we have perturbed the screening charge that are screened upon the polarization. So we did also a comparative study on lithium tantalate that was provided by my colleague Professor Yasuo Cho at Tohoku University. And you can see up rows and down rows showing the same information with using different markers. The top row shows the CGM images, the down row shows the PFM image. And the scan rate above was 40 Hertz, down was 1 Hertz. Many people use very small force in the fear that they may destroy the tip or the sample surface. So if you don't apply enough force, you will see nothing, as you can see there. But as you gradually increase the force above 100 megapascal in pressure, you start to see desorbing these ions that were absorbed on top of the surface, and it increases linearly up to the point when you start to wear and tear the surface. And that's a regime 3 in this slide. So you will see this is how the scraping occurs. Now, as a function of scanning speed, as you may expect, because you are scraping fixed amount of charge, so if you increase the frequency, the scan rate, the current will linearly scale with the frequency, as you can see in our images. So with our invention of CGM, we were able to create a new cycle of transduction of mechanical energy to chemical energy to electrical energy. As you can see on the left part of the slide, you see after the scraping, you see a change in the EFM showing a very clear contrast. But if you repeat the EFM image again and again and again, it becomes blur and blur, indicative of getting back to the thermodynamically stable phase where you have fully screened surface. Therefore, like on the right side of the cartoon, we are creating a cycle of creating unscreened surface and then rescreened by the environment and so on and so forth. So this type of new transduction cycle can be implemented into piezoelectric energy harvesting. So let me revisit the piezoelectric energy harvesting, where you apply pressure to your materials and squeeze charge out of the system by the fact that you change the polarization by stress, and therefore the screening charge will be, the requirement for screening charge will be different, so you are spitting out or getting back your charge, which is really small. How can we maximize delta P? So one example was found by flexoelectric effect or stress-induced polarization switching, presented by Alexei Grubman in his phenomenal science paper. So we were thinking, can we really change the polarization by mechanical stress, in which case we can gather a huge amount of screening charge. But that was very limited because flexoelectric effect is one-way road. You push and switch one direction, but if you want to make it back, you have to push it from the other side, which is very challenging. So we came up with the CGM idea where you squeeze and then scrape. So you can have half as much as 2PR, but that's already 100 times more than piezoelectric effect. So we tried to find if we can apply our CGM to softer materials like PVD, FTR, which is a polymer for electric thin films. We pulled artificial domains up and down using the technique that is popular in the field. And then we obtained the EFM before and after. As you can see, we had a change, reversal of the EFM signal. And we were modeling that using finite element modeling, as you can see in the following slide. And we found we were just partially scraping the charge, and that's why we had this reversal of phase contrast. And in addition to this partial scraping, we also had a problem with degradation of the CGM signal as a function of CGM scans. After 20 cycles, worst on top, we weren't able to get any more signal. So we had obvious challenge with the polymer film, which is not the case with the ceramic thin films. So now we are in the stage of scaling up our technology from AFM tip to something that is macro scale, and we are also trying to adapt the surface coating technology used for hard disk drive, where they use PFPE to lubricate the surface, and that's also analogous to shaving industry, where you put a lotion to shave your beards, also doing multiple blades with atomic radius, so you can apply high pressure over a large area and do multiple blades to get more and more charge from the surface. So this will be the future direction of applying materials imaging through charge gradient microscopy to higher efficient mechanical energy harvesting devices. Now this slide will show you the overall arching vision slides, which schematically depicts how we are going to push our vision forward. So we will not limit ourselves to AFM. We will gather all the information from TEM, SEM, STM, optical microwave, X-ray, STM, SPM, all the visualizing tools together, use big, smart, and deep data approach to extract useful knowledge and apply them to information storage, clean water and energy, food engineering, materials at extreme environment, and brain initiative, to name a few, to make a huge impact in the future. So material science and engineering in the 21st century, in a nutshell, will still keep structure processing property pillars intact, but the details will be different. So for processing science, I think putting the atoms, we want them to be at atomic precision will be the future direction. Structure property relationship will be a whole new thing at the multi-scale with the imaging and also machine learning capability. And modeling, imaging, and informatics will go hand in hand with the big, smart, and deep data approach to enable us to go to the next level. So this work was done in collaboration with my collaborators listed in this slide. So I'd like to thank all of my collaborators, and I'd like to thank for your attention. どうもありがとうございました。감사합니다.